Euclid's Elements, Book 3, Proposition 28. In equal circles, equal straight lines cut off equal circumferences, the greater to the greater and the less to the less. So it's given that we have two equal circles. Okay, we'll call this circle ABC equal to circle DEF. That's our first given. So circle ABC is equal to circle DEF. And if we have equal lines within these circles, so it's also given that BC is equal to EF. From this, we will prove that they will cut off equal circumferences. Namely, circumference BAC will be equal to EDF, and circumference BC will be equal to EF. So that's what we're going to prove. That equal straight lines and equal circles cut off equal circumferences. So circumference BAC will be equal to circumference EDF, the greater to the greater, and the less will be equal to the less. The lesser circumference BC will be equal to the lesser circumference EF. So the first thing we're going to do is take the center of the circles. So let's have G and H. And we want to connect all of these. And so let's mark what we know, right? We know that this is equal to this. That's a given. Our circles are equal. That's a given. We know that since the circles are equal, that these radii are all equal to one another. So when we look at these two triangles, we should be able to see that we've got side, side, side equal to side, side, side respectively. And when we have that, we know from Book 1, Proposition 8, that's our side, side, side theorem, or proof, that the triangles are equal in all respects. And particularly, we want to look here at this angle here. The angle at H is equal to the angle at G. Then, Book 3, Prop 26 says that if we have equal angles, they stand on equal circumferences. So in equal circles, equal angles will stand on equal circumferences, which means that circumference BC will equal circumference EF. So that proves the second portion here. And now all we need to do is, since these lessers are equal to each other, and we know that the whole circle is equal to the whole circle, if we take equal circles and we remove equal lesser portions, then that which remains, these greater circumferences, must be equal. So this is common notion 3. So if we take equal circles, so circle ABC, and we subtract circumference BC, then what remains is circumference BAC. And that will be equal to, if we take circle DEF and subtract circumference EF, then the circumference that remains, the greater circumference, EDF, will be equal. Therefore, since these circles are equal and we're removing equal portions, the remainders are themselves equal, and that is the first thing we're supposed to prove. So since we've proven both of those things, we can conclude with QED.